Welcome. So today we're going to be discussing calculations of pH and pOH. So by the end of this lesson, you guys should understand how pH and pOH are calculated. I also want you to understand how they're similar and how they're different. So first off, we have to understand what pH is. You've probably heard the word before. You've probably heard it used in reference to something acidic, but what exactly is it? So pH stands for the power of hydrogen. So that's the P part, power of hydrogen. There's the H part, so the power of hydrogen. That's what pH actually stands for. So it is calculated in relation to the exponent, aka the power of the value of molarity of hydrogen ions in a solution. Hydrogen ions are sometimes also called hydronium, H3O+, but it's still the hydrogen ion in an aqueous solution. So sometimes you'll see it referred to as H+, sometimes you'll see it referred to as H3O+, but it's the same thing, it's hydrogen in water, okay? So the exponent on the value of molarity for the hydrogen in that solution is going to be used to calculate the power of hydrogen. So you've probably heard of the pH scale. The pH scale ranges from 0 to 14. So all of your pH values should be in that range from 0 to 14. So right in the middle of the pH scale is going to be the value 7. Now that represents a neutral solution. And in a neutral solution, what we have is we have an equal amount of hydrogen ions, aka acidic parts, and hydroxide ions, aka basic parts. So when those two concentrations are equal, we have a neutral solution, and the pH that's calculated for that neutral solution is going to be 7. Anything less than that, so anything less than 7, is going to be considered acidic. And so in an acidic solution, what we have is we have more hydrogen present than hydroxide. So the concentration of my hydrogen ions, or hydronium, is greater than the concentration of hydroxide. On the flip side, if we have a pH value greater than 7, then that means we have a basic solution. And in a basic solution, our hydrogen ion concentration, or hydronium, is less than the concentration of hydroxide. So my acid parts are less than my base parts. So then let's talk about how we calculate this pH value that ranges from 0 to 14. So the formula for pH is the negative logarithm. Don't be scared, it's just a button on your calculator, okay? It's the negative logarithm of the concentration of hydrogen ions, or hydronium, however it's given to you. So you see this H plus in brackets, or it might be, H3O+ in brackets, same difference, okay? That represents the molarity of hydrogen or hydronium. So instead of putting an M, a capital M for molarity, we just put that concentration inside of brackets, and that represents the molarity of that solution. So when you see something asking for H plus in brackets like that, they're asking for the molarity of hydrogen. Or if that value is given to you, if it says, bracket H plus bracket equals, then what comes after that is the molarity of that solution. So we need to calculate the pH of a solution. This is going to be the example. First off, we have to look at what we're dealing with here. What we have here is an acid. And what we know about acids is that when we put HCl into water, it is going to dissociate, because acids dissociate just like ionic substances do. So it's going to split down the middle, and what we're going to end up with is a hydrogen ion and a negative chloride ion. Those are going to be floating around in the water, just like ionic substances dissociate, and those ions float around in the water. So if we think about this in terms of molarity, whatever the concentration of hydrochloric acid was, I'm going to get that same concentration of hydrogen ions. I'm also going to have that concentration of chloride ions, but those really aren't going to affect anything here. They're not used in our calculation. So what we can assume for strong acids that dissociate 100% and form ions 100% of the time is that whatever molarity is given to you for the hydrochloric acid, that same molarity is going to be used for the hydrogen concentration. So basically what I need to do is take this molarity that was provided and plug it into this formula. So I'm going to put negative logarithm, and then I'm going to type in my calculator 5.0 times 10 to the negative fourth. Now before we even get started with this calculation, before I even turn on my calculator and punch some buttons, I want you to understand that the power of hydrogen is coming from that exponent right there. So whatever answer we get, it's going to be pretty close to the number 4. And it's going to be a positive value because you see this negative in our formula right here. That's going to get rid of the negative here, and we're going to end up with a positive value for our pH. So keep in mind before you even start a problem that whatever value for pH you calculate, it should be pretty close to the exponent on the molarity for your hydrogen concentration. So let's go ahead and just type it in. I'm going to hit negative, then I'm going to hit the log button. It's literally just a button on the calculator. So I hit the negative button, I hit the log button, and then I type in 5.0 times 10 to the power of negative 4 and hit enter. And so what I end up with is a pH value that's equal to about 3.30. Also, a side note about significant figures and pH. So significant figures start after the decimal value for pH. So if I had 2 significant figures in my value that was provided to me, I'm going to keep 2 decimal places in my answer. So my answer is going to be 3.30. And that's not too far off from the number 4. So that leads us to believe that this is a correctly calculated pH. Now, eventually we're going to be relating acids and bases to each other, and a concept that's going to be really important to that is something called normality. So for diprotic acids, such as H2SO4, that have 2 hydrogen ions, aka 2 protons, right? Because that's basically what a hydrogen ion is. So because this acid has 2 hydrogen ions that could dissociate, it's known as diprotic. There are even triprotic acids, like phosphoric acid, H3PO4. Normality is calculated by taking your hydrogen ion concentration and multiplying it times the number of hydrogens that are in that formula. So for example, if I had a 1 molar solution of sulfuric acid, I would take that molarity, right, my 1 molar, and I would multiply it times 2 because there are 2 protons, aka 2 hydrogens, that would dissociate in that formula. Now be really careful with this. Let me give you a non-example. So one of the acids that you guys might see is acetic acid. So it's HC2H3O2, and you might be thinking, oh, there's 4 hydrogens in this. So if I wanted the normality of this, then I would take, my molarity of acetic acid and multiply it by 4. But be very careful because the only hydrogen that actually dissociates, that breaks off and floats around in water, is that first hydrogen. So if you see a hydrogen well within a polyatomic ion, right, it's hidden here inside of this acetate ion, those don't dissociate. So not all of the hydrogens will dissociate. My trick is look for the ones up front. If it's an acid, it's going to be the H's up front that dissociate. So see here we have 2 hydrogens at the front of this formula. Then to find the normality of sulfuric acid, I would take its molarity and multiply by 2. For phosphoric acid, I would take its molarity and multiply by 3. For acetic acid, I wouldn't do that because it's only going to be that 1 hydrogen up front. So the molarity of the acid is going to be equal to just the molarity. You don't multiply it by anything. So the normality wouldn't be any different for acetic acid than it is for the molarity. Okay, so now let's talk about how we can go backwards. What if I have a pH, but I need to figure out what the molarity of hydrogen is in that solution? So to go backwards, to take your pH and turn it back into a hydrogen ion concentration, we're going to use base 10. So it's actually the same key on your calculator as the logarithm. You would just hit second and then the log button, and you'll see a 10 pop up with an exponent. And the exponent you're going to enter in is negative and then whatever pH value you were given. Okay, so for example, If I wanted to come back up here, if I knew that the pH of this solution was 3.3, and the question was, what was the molarity? Then I would, in my calculator, hit second log and bring up that base 10. So I'd see the 10 in my calculator, and then for the exponent, I would put negative 3.3. And then that would give me back roughly the same molarity that I started with. In fact, we can try it here. If I do base 10 negative 3.30 in my calculator, so second log brings up that base 10 button, and then I put negative 3.30, I end up with 5.0, and then there's a bunch of other numbers, but we're keeping two significant figures here. So 5.0 times 10 to the negative fourth. That would be the concentration of hydrogen in my solution. Okay? All right, so again, I guess here's another example. Calculate the molarity of a sample of hydrochloric acid with a pH of 2.6. So again, if the pH is known, then we're going to plug that into this formula right here, and I'm going to do base 10. So I'm going to hit second log and bring up that base 10, negative 2.6. And so if I do that, second log brings up base 10, negative 2.6. Then I get an answer of 0.002511, blah, 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 blah. If I look at it, this was a pH value and there was only one decimal place after, so that means I'm only going to keep one significant figure, which means that I'm keeping this first sig fig, this first non-zero digit in my value. And so if I round that, that's going to be 0.003 would be the molarity of the hydrochloric acid in this solution. Okay, so now let's talk about pOH, which is really not discussed very widely outside of chemistry. But basically, it's the same thing, just using hydroxide. pOH stands for the power of hydroxide. And so hydroxide, of course, is OH, and so that's where pOH comes from. It's the power of hydroxide. So when you have a basic substance that has a given hydroxide ion concentration, then you are calculating pOH rather than pH. So pH is generally calculated in terms of the hydrogen concentration, and since acids produce hydrogen, then basically you're doing this with an acidic substance. If you're given a basic substance, then you are going to be calculating the power of hydroxide. And so the pOH scale works a little bit differently. Now 7 is still going to be neutral, where the concentration of your H plus is equal to the concentration of your hydroxide. So they're the same. However, anything less than 7 on the pOH scale is actually going to be basic, because you have a greater amount of hydroxide than hydrogen. Anything greater than 7 up to 14, and again, the range is from 0 to 14, that means that it's going to be acidic, and your hydrogen concentration is greater than your hydroxide concentration. So it's flipped around. Okay, so anything less than 7 on the pOH scale is basic. Anything greater than 7 on the pOH scale is going to be acidic. pOH is calculated using basically the same formula as pH. It's going to be the negative logarithm, but this time we're going to use the concentration of hydroxide ions. And that's going to give us our pOH. Okay, I didn't provide an example to you because basically it's the same thing as hydrogen. You're just doing this for substances that have a given hydroxide ion concentration. Most of the time those are going to be bases. So question is, how can we convert pH to pOH? So how do we go back and forth from one to the other? Well, they are actually related, because if I add together my pH and my pOH, the sum of those two values is going to equal 14. And that has to do with this thing called Kw down here, but the sum of those two values is going to be 14. So I can figure out one and the other by doing some simple subtraction. If I take 14 and subtract my pH, then that's going to give me the pOH. Similarly, if I have 14 and I subtract a given pOH, then that can give me pH. So it's very easy to take one and convert it to the other. So if you're given a basic substance and you calculate your pOH using this formula, but they've asked for pH, it's very easy. You just take the value you calculated, subtract from 14, and that'll convert it to pH. Now we can also convert between hydrogen ion concentration and hydroxide ion concentration. There's a value known as Kw. It's the ionization constant for water. And it is equal to 1 times 10 to the negative 14th power. See the power of 14. That's where this is coming from, right? And it is equal to the product of my hydrogen ion concentration times my hydroxide ion concentration. So if I multiply those two molarities, then that gives me Kw. Similarly, again, mathematically, if Kw is a constant, it's always going to be 1 times 10 to the negative 14th. So if I take that value and divide by H plus, that'll give me OH minus. If I know my hydroxide ion concentration, then I can take Kw, 1 times 10 to the negative 14th, divide it by the hydroxide ion concentration I've been given, and that converts it to hydrogen ion concentration. So instead of subtracting, we would be dividing here, but as long as I know 1, I can take this value for Kw, 1 times 10 to the negative 14th, divide it by the one I've got, and that's going to give me the other. So we can actually compile these formulas all together down here. It's kind of tough to see on this screen. Sorry about that. Let me see if I can maybe make it a little, nope, not that. Maybe make it a little smaller. Nope. Oh, just clicking everything over here. Let me see if I can make it just a bit smaller. Nope, that actually made it harder to see. Okay. Nope. Okay, we'll just blow it back up. So here's what we can do. We can kind of compile all of these together. And so if I have my hydrogen ion concentration and I want to turn that into a pH, then I am going to negative log my hydroxide ion concentration, or my hydrogen ion concentration, sorry, and that would turn it into pH. If I want to go backwards, if I want to go this direction and take pH and turn it into H+, then I would use base 10 and then negative pH. I'd put that in there. Okay. Again, if I have hydrogen ion concentration and I want to turn it into hydroxide ion concentration, we can use Kw. So here I would do 1 times 10 to the negative 14th divided by the one I know, the one I have a value for, and that would give me the other. So to convert between one and the other, I could take Kw, 1 times 10 to the negative 14th, divide it by the one I've got, and that flips it around to the other. If I have pH, and down here in this corner it would say pOH, if I have pH and I want to convert it to pOH or vice versa, I would take 14, subtract the one I know, and then that would equal the other. And then down here at the bottom, we can relate pOH and hydroxide ion concentration. And again, it would look a lot like this line up here. If I'm going from my concentration to pOH, then I would use the negative log function. And if I'm going in the opposite direction, which I'm kind of out of room on, if I've got my pOH and I want to turn that into hydroxide ion concentration, then I would do base 10 negative pOH. And that would give me my hydroxide ion concentration. So you can relate all 4 of these values to each other mathematically. Use this tool down here to help you out with this, and I hope this helps with your calculations.